Swayam Prabha. Digital India. Educated India.
The next presentation. The final presentation in this session is this one. Okay.
My name is Lokesh. I'm from IIT Madras and as part of CNI group. We actually work on a lot of unsupervised learning techniques. Here I'm going to present work on time series data because it's of interest to process engineers. This particular study that I'm going to talk about is a small study that we did for Dassault Aviation in an unsupervised approach. But I can, towards the end, I can mention how it's used in process systems engineering. There are the papers by Babji Srinivasan on how this can be used for control loop assessments. So, just a show of hands, how many of you are non-chemical engineers, please? Non-chemical engineers, please? Okay, thank you. So, this is joint work with Dassault Aviation. So the data set that we got is from Dassault Aviation and what they are doing. So, I just give a background of about the project, then talk about some of the techniques that we use here, about multifactorial analysis, why we think it's useful here. And we're going to use a technique called generalized progressive analysis. I will go briefly over it and I can go into mathematical details towards the end if somebody needs. And just walk you through some results and future work. So as I mentioned, basically this is a collaboration with Dassault Aviation, and what they did is they gave us a bunch of flight data from sensors, some pressure sensors, temperature sensors, altitude data, and they didn't say anything about it. They said basically now if you figure out what's anomalous in this data, how many flights are anomalous. So that's all the domain knowledge we have. They said basically it's not even a big data, like 50 data sets. You cannot do any deep learning. So I said, okay, come on, you do whatever you want. And so they said, okay, fine. So this is what we do. And okay, this is how your data would look like. And so this pressure data and this is temperature data. So you have about 50 data sets like that approximately with about 7 sensors. And so we said, okay, fine, this is all we have, then what's a normal behavior and what is anomalous behavior? And so we said, okay, then we see some time series data and let's say ECG data, right? So how do you classify a healthy heart versus a unhealthy one? And there are some techniques, so how can we bring that? And so we take that approach and we say basically one of the reasons people are able to do that in ECG is because they kind of consider the process is having multi-scale behavior, they exploit that, and even in turbulence modeling they do that. So we said, okay, why can't we try using something like this to understand if there is any shape for this data? And that's the line of, I would say the take that we take on this project. So what we try to do is basically, as a multi-factor analysis is more like a mathematical microscope to look at multiple scales. I will go into details a bit later, but what I wanted to show is it's being used extensively in ECG data. You say basically healthy heart versus basically some patients, as you can see the plot here. And it's also been used to kind of predict financial crashes. And in a lot of other cases, for example, the last one, you see actually you are able to predict a combustion instability before it even sets in, looking at the collapse in the multifractal spectrum. And actually this is a big deal because basically if you are able to do that, it's $1 billion industry to be able to predict the instability even before it occurs and kind of damages your components. So we said, okay, let's use this technique, and as you can see here, the green lines correspond to the multifractal spectra of the healthy heart, and the red ones are the patients. There is, I would say, there's there are overlaps and things like that, but there is some as in distinguishing. There are actually there's some, at least some regions where they are very different actually. So what you want to do is you want to at least try to capture this to see if it's helpful. For example, when there's a cardiac arrhythmia, this whole multifractal spectrum, which is actually it is a very broad support, collapses to a single point actually. So, but then in the middle between a cardiac rhythmic case and healthy heart case, I would say there's a spectrum of a lot of cases where gradually the spectrum collapses. The support of the spectrum collapses. So So what do you do in multifractal spectra is you take the time series and kind of you mean center it. Then what you do is you kind of start splitting into segments. For each segments, you do a polynomial fit and detrend it. Once you have these fluctuations, you look at something, a variance-ish approach. It's a LQ norm, and then this particular quantity will actually, for example, if your scale is S, it will go as S to the power of HQ, where H is the generalized Hurst exponent. When Q is equal to 2, it's called the Hurst exponent. And I'll just walk you through a small example of how this is done. So let's say this is the time series. And then you kind of, we have cumulated it because basically we wanted to kind of, when integrating basically we want to eliminate the errors, we get better approximations. And so then we kind of segment it using one scale here. So S is a scale. And then the red lines, what you see is the fits, and the blue line is the original time series. The next step is we detrend it. And after we detrend it, these are the fluctuations of each one of the segments. We calculate the variance, as in the, I would say, the F, the fluctuation coefficient. And basically what we try to do is basically, this is for one scale. So what happens is we kind of take the average of variance on all of this. And then what you do is you do the same thing for multiple scales. So what you get is, this is what you get. So basically what you just saw is one point here. Now if you do for multiple scales, what you get is A, I would say, on this whole line. Now, in the case I showed you, basically there's a Q exponent, it's a LQ norm, so you can vary Q. So you can vary Q from negative values to all the way positive. And what happens is, why is it called a mathematical microscope? Because when you take the value of Q that's negative, what happens is it magnifies the smaller fluctuations. So you know what's happening at smaller scales. When you take a Q value that's very high, basically it magnifies the larger fluctuations. So you know what's happening at with bigger fluctuations. So in a way, depending on the scale that you want to see, you can actually tune the parameter Q and see how the behavior goes. And what is actually this quantifying? So basically what's happening here is, when you actually look at this time series, so what you see is basically, let's say you take any 2 points, okay, as adjacent to each other, then basically there's a jump in the value. So the jump is basically the amount of discontinuity. So let's say basically you can say that basically quantifying the singularity at that point, let's say. So basically let's say the jump is, let's say K, let's say. So there's a, for example, and this K can vary over a broad range of this kind, basically the strength of singularities. So what happens is you look at all the points that have the same strength of singularity, and so basically what you get is you don't get a continuous set of points, you get a discrete set of points all over the place. So you have something like a dust of points basically. And now you look, ask, how do you measure this? So the way to measure this is basically this set will have a fractal dimension. So what you do is you use what's the measure on this set? What's the point basically and then you say basically for this particular singularity strength, this is the measure of the set. And that's what we are actually trying to quantify. And this is the spectrum that you see. But getting this, computing this directly is difficult. So what you do is basically, it's proven that from the previous approach where we actually computed the fluctuations, then we actually plotted this plots varying over Q. What you can see is basically you can actually do HQQ, where HQ is the slope of this line for a value of Q. And then you use this this is actually a connection between this averaging approach with the multifractal formalism, where tau is the generalized it's an exponent, multifractal scaling exponent. And then you do a Legendre transform, and you can actually get Q, where alpha is the strength of the singularity, and F of alpha is the measure of the set. But because it's difficult to directly compute this, you go about this whole procedure, and you actually get the same. So this is in a nutshell, but actually I can discuss with you in detail later. But what I want to do is, I want to use this as a tool to look at this data. What happens when I use this as a tool? So this is what happens. So basically we took those 50 time series and we actually try to plot the multifractal spectra for all of them. And as you can see clearly, some of them are deviating very far off from what is considered as a norm. So what does this mean? We'll come to that later. But as a now, how do you quantify this? Which is anomalous and which is normal? So then, what we want to do is, at this point, we want to kind of quantify the shape. What's the mean shape of this? So what you try to do is basically use progressive analysis. Progressive analysis, generally what it tries to do is, you have two shapes. You kind of see basically how different these two shapes are. So what you do is, first you take two shapes and basically you say translate at the origin, and they're overlapping. Now what you try to do is scale them, for example, and see how the scale disparity is. Then you rotate them so that basically the norm becomes minimized. And then after having done all of this stuff, what you have is basically, if there's some disparity, that's called the shape disparity. So this is all it does. And for example, progressive analysis, if you can take two shapes and do that with two shapes. But if you have I would say, a lot of shapes, like n number of shapes, and you want to do that, you do a generalized progressive analysis, and this actually gives you what a mean shape looks like, and then you actually compute the disparity with respect to the mean shape. And so here is one experiment that we did. There are two masks of two different individuals, same as two point clouds, and after having done all the transformations that I told you, then this is what happens. There's some disparity that can be quantified. So this is what we did, and we took all those shapes and we kind of collapsed them and kind of try to get what's the mean shape, and this is the mean shape from the GPA. And now we use this to be able to kind of compare everything against this one and see how the disparity looks like. And this is what it looks like. For example, as generally most of the things deviate around like 0.4 or something, the deviation here. But then you see some points way up here, like case number 17, case number 26, case number 39, so on and so forth. As you can see, some deviations here. We actually captured this deviation and we saw basically what's happening here. And the pressure sensor is malfunctioning apparently, so it's not working well. So what's happening is it's actually capturing some level of anomalous behavior in the sensors actually. This case actually, so what we want to say is, we don't have any ground truth actually. It's totally unsupervised, and there's nothing to, I would say, benchmark against. So we said, okay, let's get something to benchmark against. The next step we did is, okay, let's look at how would you conventionally do this. Okay, you have some time series, you probably construct an AR model to see what is the equation governing this at least. And this is what we see. This is the AR model, and this is the one that came up with multifractal along with GPA. And what you see is basically some of the things that are flagged by AR models are also flagged by the 17, for instance. Some of the case IDs are listed, 47970. And other than that, there are some things that have been flagged by AR models which have not been flagged by MFGPA. And similarly, the vice versa. There are some things that are flagged there which are not flagged here. So at this point of time, we see that it's a promising tool, but we don't totally understand what's happening underneath, why it's flagging some which is not flagged by AR models or vice versa. That is under investigation. But we see this as a promising tool to be able to look at, let's say you don't have any information on the data or how it's generated, just in a totally unsupervised way. I would say this actually is a promising tool for us. So this is able to flag anomalous flights, one thing, at least some of them, but then there's disparities. We need to verify ground reality at this point of which we don't have any access to. And the third thing is basically at this point of time, I just use one time series. I told you there's 6 sensors to 7 sensors. So you can actually get a much robust estimator, but how do we do that? So we don't have techniques to do that. And the next step we want to do is extend this. So actually I can take any questions, or I can actually, there's GPA, these are the, for example, in the disparity, what happens is you can see the disparities, the contribution of each disparity. How much translation contributes, how much rotation contributes, and scaling contributes. Here's the breakdown. And these are details of the generalized progressive analysis. Here is the translation component, which I translate everything so that it comes to the origin. The second thing is scaling component. Then you compute the scaling disparity, where you take the distance from all the points, kind of sum it up, take the average, take the root, and basically this is more like the average distance. You use that to scale the whole thing up here. And the next one is the rotation. So after having done all the transformations, these are your transform coordinates for, let's say, one point cloud A, other point cloud B. Then what you try to do is basically, when you write Superim, what you want to do is you want to minimize the norm and basically the distance. Basically here's the Frobenius norm, this one. And so what you and omega is the rotation transformation. It's an orthogonal matrix. And then you want to minimize this one. And so what is that omega that gives me the optimal one? And the answer is U transpose V, where U we come from the SPT decomposition of dA transpose matrix. And having done all of this, you have translated one, you have scaled it also. The second one you translated, you have scaled it, and then you have rotated. After having done all these transformations, if the point clouds still do not align, Then the distance you compute, the total distance that you compute is basically this one, and it's called progressive distance. This is what is called shape disparity. This is what we use to compare the spectra, the mean spectrum. So I think, yeah, I'm done with any details you want me to catch up. Thank you.
Any questions?
I want to ask one short question. Yeah, I want to see the data that you have.
Yep.
Multiple curve used in P and GPA. No, next, and next. Yeah, here. So here the green line would be. Yeah, I think this is outlier. So yeah, in all detection methods.
I think this is case number 7.
That you include the analysis that using that data, right? That yeah. So in this analysis, we should include the data such, for example, abnormal ones or the.
I get your point. So basically, you're saying the mean spectra is going to be distorted by the abnormal ones, so you don't know what it is. So it is like a priori, we don't know that, right? A priori, we know what's abnormal, what's normal. But we expect that as in bulk of them are normal and 1 or 2 are abnormal, and hence basically when you do the mean, it comes towards the normal. They'll definitely be affected by abnormal ones, but yes. But it will be nice if we had what's that normal operating things. Basically, when you kind of try to do something unsupervised, you have no information whatsoever. You just given a bunch of time steps.
Maybe we can determine that the left side curve is more normal.
No, I get your point. That's what it's like. So what we can do is basically after we have plotted this, right? After we have plotted this, here. After we have plotted this, you can eliminate all of this, and then reconstruct your mean GPA, and then you do, and then actually this will deviate even further. So, but then you can color some more points. Yes. But as in generally, the main problem is basically when you do, I would say, machine learning. So what happens is you have a very specific loss function. You know what the ground truth is, and you penalize it, whatever you get against it. We don't have anything like that here. So that's a problem. And so this is the best we can do as a first cost solution, then iterate it and kind of that's what.
Okay, thank you.
Questions?
So anomaly detection are mostly kind of unsupervised way of detecting.
Sure, yeah.
So how we will find out in the real time that okay, whichever are anomalous or whichever are non-anomalous are correct?
I'll tell you one thing about here. Basically, I want to kind of draw your attention to the first data. I showed it here, right? This one. So what happens is, how do you know? At least we have some domain knowledge here. The domain knowledge is basically, as in this methods apply to things that actually have multifractal nature. What does that mean? There's a lot of scales, and there's some kind of energy transfer that happens from bigger scales to lower scales, following some physics. But this kind of physics that happens at this scale and this scale is different. You're getting my point. So now, what you can actually here, what we do is basically when you actually look at a multi-scale behavior, you have a broad-based spectrum. Like for example, the support of the spectrum is very large, right? If you actually, this is for the heart, it's unhealthy. If you actually plotted the same thing for a combustion engine, as it is going towards the instability, what you see is this support goes from here, it goes shorter, and collapses to a single point. So looking at the spectrum, you can actually basically kind of look at the support of the spectrum, you can say, at least get an idea of how far you are from the breakdown. So, and then you can pull the machines on. So basically that's the reason why it's more important in process engineering. And so what you can do is, for example, if you're actually looking at the Hurst exponent, forget about q or whatever I told you. Just take q is equal to 2 in the equations, f of the function I showed you here. You just take q is equal to 2 and you compute the whole thing. And then what you do is basically you kind of look at how, I would say, let's say you detrended your signal, whatever, and what happens is basically if it is a white noise, at the end, when you actually have a good controller, your residue should be white noise, right? When you have a white noise, basically this h of q, the exponent will be 0.5. If you have something that's more than 0.5, like 1 or something, that means you have a signal they have long range correlations. That means you can extract more information out of it. That means you have more predictive power which you are unable to do it. So what happens is basically in these systems, because there's at least the only domain knowledge we use is multifractal behavior. Once you use that, you have some predictive power looking at H. If H is like 1 or something, you have long range correlations. If H is 0.5, you have, as a null say, it's like there's no correlations at all. So that we use actually. So